we say last time, here is the here is a table for all the properties of a discrete time Fourier series. And again, a small review. Last time we described this discrete Fourier series. It's very similar. Let me go back a little bit. Okay, so here we have the synthesis equation and analysis equation. It's very similar to the continuous time case, except obviously the x is not discrete time, and and we think that because x is discrete time, so ak is kind of periodic. So we see that if x is periodic with period big N, ak is actually also periodic with period big N. Okay? And we only need to sum over ak for interval of length big N. Okay? And also there is no convergence issue for this discrete time Fourier transform. Then we go to the properties of discrete Fourier transform. And as we say, many of them are similar to continuous time case, or some of them we'll see later, like this time scaling definition. We'll see later when we talk about Fourier transform. So we don't go into detail of the table, only go through some example here. Okay, and so first example is multiplication. So we see that if we have some x of n with Fourier series coefficient ak, and some y of n with Fourier series of coefficient bk, then the signal that x of n times y of n will have the Fourier series coefficient bk equal to the summation L times b minus k. And we can see this, we can think of this as a periodic convolution. So this is a convolution for two periodic signal, because we know ak is periodic with period big N, and the bk is periodic with period big N, and so we think about the convolution of those two periodic signal is this summation over one period Al times bk minus L. Okay? And this is consistent with what we said before. So for this Fourier series or Fourier transform, if you have a multiplication of two things on one side, then you have convolution of the two things on the other side. And so here we have a similar thing. So in here, let me make it bigger. So you'll see that if you have a convolution of two signal here, then then you have the corresponding multiplication of the Fourier series coefficient here. But because of some normalization issue, you also have a big N here. Okay, so that's the convolution and the multiplication property. And the next property is different from continuous time case, is this first difference. So as a reminder, in continuous time we have that if you do a differentiation, if you do a derivative, you do a differentiation on your signal, then you will get this HR JK omega naught on your AK. Okay? And in the discrete case, we don't have differentiation, and the counterpart is this difference. Okay? And so what happens if you take this first difference of your signal is that you get this HR much more complicated factor, 1 minus e to the minus jk 2 pi over n on your AK. Okay? And this is very easy to derive, because this is just a linear combination of this signal plus minus this signal. Okay, so this signal has coefficient ak, and this signal is the time shift of x, and so you will get this HR e to the minus jk 2 pi over n factor. This is just from the time shift. This is minus jk omega naught. Okay, and then you take the linear combination of them is this coefficient minus this coefficient. Okay, and then the possible relationship is also very similar to continuous case. So here is the continuous case. You have the energy over one period in the time domain equal to summation of all the energy in all frequency. Okay, and in the discrete case is similar. So you also have energy over one period here, but now the AK is also periodic, so you also have the energy over one period here. Okay, the energy in frequency over one period of the frequency, where the period is big N. Okay, and so let's see some example of using the properties to determine the Fourier series coefficient of some signal. Okay, so here we have start with the quite straightforward example. So we ask for if we have a signal that look like this. So it's this 1 1 2 2 2 1 1 2 2 2 keep repeating itself. Then what's the Fourier series coefficient for this signal? And we decompose this signal into two signals. So we see we have this up down thing, and so we cut out this up down part. Is so the first signal is this 0 0 1 1 1 0 0 1 1 1 signal, and the signal we've seen before. This is the back wave signal. Okay, and the second signal is the rest of the signal is just a constant 1. Okay. So you can check very quickly that is x1 of n plus x2 of n equal to x of n, because well those 2 points is 0 plus 1 equal to 1, and those 3 points is 1 plus 1 equal to 2, and all of them have periodic is period 5. Okay, so the big period for those signal is 5. Okay. And so basically we have x of n with Fourier series coefficient ak, and x1 of n with Fourier series coefficient bk, and x2 of n with Fourier series coefficient bk, ck. Then we only need to find the bk and the ck, then we find ak. And bk we had the formula before, so this is a copy from the previous formula. So before we were calculating the general formula for signal looking like this, then we have that the bk will equal to this 1 over sine 2 pi k and 1 plus 1 over 2 over n over sine pi k over n. Okay, and the big N is the period here, so period we know is 5, and the small n was, okay, let me take this out. And sorry, big N, and then we have big N1. So big N is 5, and big N1 is 1. Big N1 is this number here. So this is minus N1 plus N1. So big N1 is 1 over. Okay, so yes, let me write it here. So big N1 here is 1. Okay, so we can just plug in this formula. Excuse me. So big N1 is 1 here. So this is minus 1 to 1. Okay, so you can just plug in n1 equal to 1, n equal to 5 here. And another way to see this is you look at those vectors. Okay, I think it is a bit more straightforward. Is you look at this vector. So that's or the vector that's not pi k over n is 2 times n1 plus 1 half. So it's 2n1 plus 1, and it's just a number of non-zero dots here. So it's 1, 2, 3 here. So those vectors together should be 3. Okay, and yeah, so this is for bk for k not equal to 0, and the bk for k equal to 0 is the average of this signal, so it should be 3 over 5. Okay, and yeah, so that's the result. So bk is 1 over 5 from this 1 over n, and we say it is sine 3k over 5. Okay, because you have 3 non-zero thing and period over 5. Okay, so sine 3 pi k over 5 over sine pi k over 5. And for k not equal 0, for k equal 0 is 3 over 5. As we say, it's the average of this thing. And for x2, they only has it's a constant function, so you only have the dc component, that is c0 equal to 1, and ck equal to 1 for ck equal to 0 for all other components. So for all the k not equal to multiplicative of 5. Okay, so you add those two things together, then you get your AK. So AK when k not equal to multiple of 5 is 1 over 5 sine 3 pi k over 5 over sine pi k over 5. And for k equal to 0 is this 3 over 5 plus 1 is 4 over 5. Okay, everyone okay with this example? If not, if you are good, then let's go into another example. This is, I guess, this is a form of problem that we'll see in homework and test. Okay, So it's kind of a detective case. So we give you a whole bunch of conditions and ask you to determine what's the Floater-Sheet coefficient. And yeah, so this can happen either in discrete case or continuous case. I think this is also in one of the homework problems. Okay, and anyway, so the problem looks like this. You give a whole bunch of conditions and ask you what determine. You can either ask you to determine xn or determine ak. Okay, this is very similar. But anyway, so we're going to determine ak first because as you will see, those conditions will be highly related to ak. Okay, so first we say that xn is periodic with period big N equal to 6. So we know big N equal to 6. So xn is periodic with big N equal to 6. Then we also know ak is periodic with big N equal to 6. And also this omega 9 is 2 pi over n equal to pi over 3. Okay, and then we have let's look through the condition first. So we have a bit of cryptic conditions here. So first one is the summation small n a x over n equal to 2. Then second, sorry, I should say I should talk through the range. Okay, so summation small n from 0 to 5, xn equal to 2. And then third condition, summation small n from 2 to 7 minus 1 to the n x over n equal to 1. And the fourth condition, xn has minimal power per period among a set of signals satisfying all three conditions. Okay, and the question is determine x over n. Okay, and the strategy here is that we'll determine ak first, then we use this synthesis equation to write the x over n. Okay, and why we want the ak is because the condition 2 and 3, if you think carefully, is very similar to this equation here. Okay, so condition 2 and 3 will tell you something about ak. Okay, and so first condition told you that the big N equals to 6, so there are 6 different ak we need to determine. And the condition 1 says that this summation small n from 0 to 5, but we know big N equals to 6, so this is summation over one period, right? So this is 6 consecutive numbers. So we got this summation over one period, and then we have xn here, so it's similar same as this xn here, and but we have nothing, so we are missing this e to the minus jk omega naught 0 factor. Okay, but we see that this is nice because when we have nothing here, this is corresponding to k equal to 0. Okay, when k equal to 0, this is e to the minus jk omega naught equal to 1. Okay, and so this is yeah, so k equals 0, we see that this summation here happens to be this summation here. So we know this is for k, so we know this is very related to a0. So this is 2. So now this 2 can help us calculate a0. Because a0 will be this summation, which equal to 2. So this 2 equals to this 2 here, and over n, and we know n equals 6. So this condition exactly tells us that a0 equals to 1/3. Okay, and yeah, so I guess we've shown that this corresponds to this k equal to 0 condition. And I guess if you want a bit more intuition, what can you think of this as a k equal to 0 condition? Then remember that we have been keep saying that the k equal to 0 condition is the average of your signal. And this is a DC component, and it's the average of your signal. And you see that this is the average of your signal. Okay, this is the sum of your signal over one period. I guess it's not quite average because if you want average, you need to divide by 6. But this corresponds to the average of your signal. Okay, and then the next condition here, this summation n from 2 to 7. We've seen similar thing before. Okay, so 2 to 7 is different from 0 to 5, but it doesn't really matter because here, as we said, we only need to care about summation over one period. Then yeah, so 2 to 7, you see that once again you are summing over 6 consecutive elements, so it's summing over one period again. And then once again we have x over n, but now we have this extra factor minus 1 to the n. Okay, and what is this minus 1 to the n? Okay, so when we sum over x over n, this is for the lowest frequency component. So lowest frequency component k equals 0, and this minus 1 to the n actually corresponds to the highest frequency component. Okay, because and the highest frequency component is when k equal to n over 2. Okay? Because remember when we talked about discrete signal, we said that because we are discrete, so the lowest frequency component is not talking about component. So for discrete signal, we have said that the lowest frequency signal you have is obviously it's a constant signal. And we said that we have a discrete and the highest frequency you have is you have minus 1, 1, minus 1, 1, or 1 minus 1, 1 minus 1. This is what we have been talking about in chapter 1. In the discrete case, this is the highest frequency signal. Okay, and so this minus 1 to the n as a function of n is exactly this 1 minus 1, 1 minus 1, 1 minus 1. And it's a highest frequency component, and they correspond to k equal to n over 2. Okay, because as you increase k, your frequency keep increasing, and then you kind of go back when k go to 6, then k equal to k equal to 0. Okay, and then that's the intuition, and we can also check that algebraically that minus 1 to the n actually corresponds to this k equal to n over 2, because minus 1 to the n equal to, so minus 1 in terms of complex number is this e to the minus j pi n. Okay, so it's e to the minus j pi n, and then this pi will equal to, now we write it in terms of k omega naught. So when k equal to 3, and we know omega naught is 2 pi divided by 6, then you see that this 3 times 2 pi divided by 6 is this pi here. Okay, so you see that indeed when k equal to n over 2, or in terms of n equal to 6 and k equal to 3, we have exactly that e to the minus jk omega naught n will equal to minus 1 to the n. Okay, we have e to the minus jk omega naught n, then equal to e to the minus j pi n, and e to the minus j pi equal to minus 1. So this is minus 1 to the n. Okay, and so we see that minus 1 corresponds to the k equal to 3 component, and so just like here, this summation will tell us what's A3, and A3 will equal to this 1 here, so that's equal to this 1 here, and over n equal to 6, so A3 equal to 1 over 6. Okay, and so this condition tell us A0, and this condition tell us A3. Okay, and then the fourth condition says that we need to minimize power while satisfying those conditions. Okay, and here I guess I'll talk a little more. Okay, so here this is actually a bit more subtle. So the most straightforward way is saying that we determine A0 and we determine A3. So A0 and A3 is fixed, and obviously the way to minimize this is that the AK, I guess that's do the calculation here first. So here we want to minimize power, and we know power is related to this summation. So the power of xn is the possible equation we just talked about. Okay, so power is the summation x over n squared, and I guess that's the average power over one period. And so we want to minimize this thing, then we want to minimize this summation, aka absolute value square. Okay, and because absolute value square is a positive number, so the way to minimize is that you set everything that you have not determined as 0. Okay, so summation ak square, you have a0, and here we have the possible a bit more here. Okay, so we want to minimize the power per period, so where power per period is summation x of n squared divided by n, then that equal to summation ak squared, and there's want to minimize summation ak squared, and you said all other ak are 0. So a1 equal to a2 equal to a4 equal to a5 equal to 0. And I guess here a bit of a subtle point is that the equations for ak are actually independent of each other. Okay, we have said that. So we have said that this equation will determine k a0, and the determinant equation will determine a3. And but there's no restriction on a1, a2, a4, a5, and that's because if you think about this transformation between ak and x of n as a linear transform, then each of the linear equation is actually independent to each other. So if you fix a0 and a3 with those two equations, you still have total freedom with your a1, a2, a4, a5. Okay. Oh, excuse me. Yeah. Oh, excuse me. Sorry. And yeah, so we still have freedom in choosing a1, a2, a4, a5. And I guess another way to see this is when we choose all those things, and so we pick our a0, a3, and a1, a2, a4, a5, then we can still calculate our x of n. Okay, and the x of n will satisfy those two. Okay, and yeah, so now we control our x of n from our synthesis equation as we can. So a0 equal to 1 over 3, a3 equal to 1 over 6, and all other things equal to 0. Then our x of n is a0 plus a0 term, then plus a3 times e to the jk omega n, and we know is e to the jk omega n should be minus 1 to the n. Okay, so 1 over 3 plus 1 over 6 times minus 1 to the n, and it's like this function over one period. Is this so 1 over 3 plus 1 over 6, so this is 1 over 2, and 1 over 3 minus 1 over 6 is 1 over 6. So 1 over 2, 1 over 6, 1 over 2, 1 over 6, 1 over 2, 1 over 6, and then with periodic over 6. And check again that they actually satisfy those two equations. So you sum over one period this function, then it's 1 over 2 times 3 plus, so 1 over 2 plus 1 over 6 is, let's see, is 6. 1 over 2 1 over 2 plus so summing over one period, so 1 over 2 plus 1 over 6 times 3, so that's 6, and 3 plus 1, so be 4 times 3, so that's indeed 2. And the other thing is this the other equation is this minus 1 to the n times x of n and the summation over one period. So then it's 1 over 2 minus 1 over 6, 1 over 2 minus 1 over 6, etc. So it's 1 over 2 minus 1 over 6 times 3, and that should be 2 divided by 6 times 3, and that's indeed 1. Okay, so yeah, we see that our signal indeed satisfy all the previous conditions, and they have all those coefficients set to minimum, so it should have minimum power. Okay, are we good with this example? Okay, then let's go to Let's go to the last property, the last concept of this chapter. That's about, I guess it's a bit of setup. Okay, so that's a second lecture concept. Okay, so we are talking about Fourier series, and now remember Fourier series was just for decomposing periodic signal into those harmonic components. Okay, and now we remember back our motivation for doing Fourier series because we want to analyze LTI system. Okay, so here's a bit review. So remember that we say we want to decompose things into Fourier series because we see that when we analyze the LTI system, then those complex exponentials are eigenfunctions of your LTI system. Okay? So further series for just for signals, and now we are getting back our analysis of a system, and in particular LTI system. Okay, and so here should be review. So we derive those in the very beginning of this chapter. We say for LTI system, then for conditional case, this e to the st will be eigenfunction, and for discrete case, this e to the n will be eigenfunction. And they will have some eigenvalue h of s and h of z. S is this s here, and z is this z here. Okay, and we can calculate h of s, big H of s, and big H of z from our small h of t and small h of k, and that's not surprising. Because we have said those small h of t and small h of k, those impulse responses, I should put the s here. The impulse responses, we say they totally characterize your LTI system. Okay, and yeah, so from small h and small h, you can calculate h, big H this way. So let's talk through this once again. So big H of s equal to integration minus infinity to plus infinity, small h of t to the minus st dt. And big H of z equal to summation k from minus infinity to plus infinity, small h of k z to the minus k. Okay, and now we go to, okay, so far is review, and then now we can try to connect back to our harmonic series. Okay, so harmonic series, we have that we are decomposing our periodic signal into complex exponential, but the special kinds of complex exponential where the exponent is purely imaginary. Okay, so for the analysis we have done, we have that s equal to, we have decomposed our signal into a linear combination of e to the st, with s being this either j omega, or in terms of discrete time, we have z equal to e to the j omega. Okay, and so those two equations is just putting s equal to j omega and z to e to the j omega. Okay, and you will see we have a slightly different notation because here we are writing as a function of z, so you have this be found in e to the j omega here. And this notation will make more sense later. Right now we might ask why don't we just write j omega, and I guess the answer for now is that we are actually thinking this h as a function of this complex number s, for this e to the st, and we are just restricting to a case where s equal to j omega, and here we are restricting to a case where z equal to e to the j omega. Okay, and now we can kind of see why we want to talk about this z in terms of a z instead of just like here talking about s. Because remember that in this current case we have this periodic with period 2 pi in our frequency omega. So we have that e to the j omega n equal to e to the j omega plus 2 pi n. Okay, and okay, so omega change from omega to omega plus 2 pi doesn't change your signal in the discrete case. And this property is nicely captured by writing z here, or writing e to the j omega here, because e to the j omega also doesn't change when you change it from omega to omega plus 2 pi. Okay, and yeah, so that's a kind of a small reason why in this grand case we want to write in terms of this e to the j omega instead of writing j omega, because you write as h of j omega here, then you will have a periodic function in omega. And to save us from writing the function in periodic, we just do this complex exponential. So all the omega and the omega plus 2 pi will map to the same point to e to the j omega. Okay, and yeah, anyway, that's a bit of a side note. But back to the thing we know, the thing we want to know now is those hj omega, h e to j omega, they have a name. Okay, so big H of s and big H of z are called system function. And when we focus s equal to j omega or z equal to e to j omega, then those are called frequency responses. because we are thinking about where this is a response to particular frequency omega. Okay. And yeah, so particular frequency omega, that means it's a response to some periodic complex exponential with frequency omega. Okay, because e to the j omega, as you know, is a complex exponential with frequency omega. Okay, and now back to more things we talked about at the start of the chapter. And so I guess this is a bit of a review. So we have decomposed our signal into this harmonic series. Okay, so we decompose our x of t into a linear combination of e to the jk omega naught t. Okay, and this e to the jk omega naught t is in this form, right? So if we think this jk omega naught as our s sub k, because it's indexed by k, then we see that our output should be the same linear combination because because the system is linear, and then because it's e to the jk omega naught t is an eigenfunction, so it should just map to eigenvalue times eigenfunction, with eigenvalue being h of s, with s equal to jk omega naught. Okay. So output will just be the same linear combination, but your ak is multiplied by this h over jk omega naught. Okay, and yeah, so if we have a periodic signal and we can decompose it into a Fourier series representation, then we can write down the output over a TI system by just this equation. Okay, and so we go to a direct example for doing this. Okay, so we have LTI system. And we just write it in terms of its impulse response. So we have a small h equal to this exponential decay function. So e to the minus t u of t. And here is the sketch of the function. So e to the minus t right here, and it's cut off at 0 by this u of t. And then we say we input it with this signal. It's already in Fourier series. We already calculated all its Fourier series. So x of t equal to k from minus to 3. K equal minus 3 to 3, ak equal e to the jk omega naught t, with omega naught equal to this 2 pi, and ak we are listed here. So a0 equal to 1, a plus minus 1 equal to 1 over 4, a plus minus 2 equal to 1 over 2, a plus minus 3 equal to 1 over 3. Okay, and so we want to use this equation to calculate the output y of t. So first we should calculate this h of s. Okay, so we have h of s formula before. Okay, let's go back a little bit. So h of s formula is here, or in terms of j omega, h over j omega is integration h of t e to the minus j omega t dt. Okay, so let's calculate this h of j omega integration small h of t. So this is e to the minus t, and then u of t just change your interval of integration. So instead from minus infinity, it's cut off at 0 as this u of t, and e to the minus j omega t dt. And for some reason, instead of dt, we have d tau here. So e to the minus tau, e to the minus j omega tau d tau. But t and t over tau is dummy variable, so it doesn't matter. Okay, so anyway, so this is the integration you can do. So you can combine those two factors. So you see that this is the exponential function on tau. This is e to the minus 1 plus j omega tau. Okay, and the exponential function is easy to integration. It's you pull this factor down, so you get the minus 1 over 1 plus j omega. And then you have this thing, and the upper range infinity, lower range 0. When tau equal to infinity, this thing becomes 0 because it's an exponential decay function with this negative real part. So when infinity this is 0, and when 0 this is 1 because e to the minus 0 equal to 1. So this thing is so by its lower bound, so it's minus 1. So in the end you get 1 over 1 plus j omega. Okay, and anyway, so with a lot of arithmetic, you get h over j omega equal to 1 over 1 plus j omega. And now we can plug in this into our formula. So we have our y of t equal to the summation bk, and e to so same Fourier series coefficient, same e to the minus jk omega t, which is equal to jk 2 pi t. and bk will be this ak times h of jk omega naught. Okay, and so we are separating this into many pages, but anyways, here is we combine everything. So pk equal to ak h e jk omega naught, and h of j omega is 1 over 1 plus j omega, and so kind of combine this with our omega being k2 pi, then is 1 over 1 plus j k2 pi. Okay, and so we see that for different k we have a different bk. So b0 equal to this 1 because k equals 0, you have a non-this vector, and for k equal to plus minus 1, then you have the HR vector here. You have it equal to a1 and a minus 1, so it's 1 over 4, times this HR vector 1 over 1 plus minus j2 pi, and then we have k equal to plus minus 2, then you have plus minus 4 pi here, and k equal to plus minus 3, you have plus minus 6 pi here. Okay, and yeah, so here is just combine algebra, and in the end you see that this is your b3 to b minus 3, and we can combine all these together, and yeah, you will get some function. Okay, some function y of t. Okay. Oh, this is a bit confusing, but this function is actually not y of t, because y of t is periodic signal with periodic 1, so it's another signal. This signal is what we are going to talk about here. Okay, and yeah. Okay, so we got our y of t, and so yeah, you got the Fourier series coefficient of your y, and you can combine it back to the time domain, so you get your y of t. Okay, and so but now we need to say something. Okay, we need to say this this co-calculation we do here does not always work, because this is a bit funny, but sometimes you have an input and you don't get converging output. Okay, and in particular, when you want to do this, then your h of j omega must be well defined and finite. Okay, and yeah, and let's go back. Oh, we have it here. So remember, our h of j omega is this integration minus infinity plus infinity, small h of t to the minus j omega t dt. So we want to use this formula, then obviously your h of j omega needs to be a finite value. And it might not be finite value because you have an integration from minus infinity to plus infinity. So your h of t is beta enough. So here is the example of beta h of t. Your h of t look at this, then your integration from minus infinity to plus infinity will become infinity. Then your big h of j omega is not finite. And then yeah, in chapter 4 and 5 we'll see that if you want the h of j omega to be well defined everywhere, then that means your system must be stable. Okay, and and remember, our characterization of a stable system in terms of a small h is that the integration of a small h, absolute value of small h through our minus infinity to plus infinity should be some finite value. And you can kind of see that it makes sense here, because if you have absolute value of h, integration over minus infinity to plus infinity is finite, then you add the HR phase factor, and the integration it should still be finite. Okay, and if it is not finite, and obviously this thing will diverge at omega equals to 0. Okay, and yeah, so that's the that's the Fourier series LTI system. We see that you can we can use the Fourier series representation to quickly calculate the output of an LTI system. Okay. Yeah. Okay, and then finally we can go to the test topic we want to say in this chapter, that's filtering. Okay, so filtering basically, I guess is an application of the analysis we have done in this chapter. So we just say that if we write our signal in Fourier series, then we can see the output as the input signal, but with every harmonic component being multiplied by this h over j omega. And now we can think of this as a way to design our system because, well, what our LTI system do is we just change this big H over j omega, right? And then we can think about, we can design the big H over j omega to do the thing we want, and that's kind of called filtering. So filter is a system that will change the relative amplitude of different frequency component of the signal. So the frequency component are those AK e to a JK omega naught t. Okay, so we change AK to different BK with a different relative H. Then yeah, we can change, we can shape the output. Okay, and as we see that we'll see in more detail in this section that the filtering can be accomplished through you design your LTI system with appropriate truth and frequency response. Okay. Yeah, you see the LTI system. Well, LTI system can give you different big H, and that give you the desired effect you want to have on this big H. Okay, and I guess then let's start with the example we kind of see. Okay, I guess this is a different way to see the previous example we've seen. Okay, so first we have a frequency shaping filter that's kind of basically everything. Okay, so LTI system change the shape of spectrum called frequency shaping filter. Okay, I guess the name is not too important, but let's kind of see the concept here. So for example, we have differentiation is an LTI system. So differentiation is that you have x of t, then output y of t will equal to dx dt. Okay, and we try to see how what's the big H for differentiation. And so if you use the formula before, it will be pretty hard. Okay, so the way we do this before is we find small h, then we use the formula to find big H. And but here we introduce easier way to do this is we know big H is the big H of j omega is just the eigenvalue of e to j omega t. So we just put the x of t equal to e to j omega t and calculate y of t because we have explicit formula here. So x of t equal to e to j omega t. Then y of t is dx dt. Then you get h j omega factor and then still get e to j omega t. And you compare these two, then you see that the big H is the thing here. Okay, big H is big H of j omega is this j omega here. Okay. So this is another way to calculate the big H of j omega. It's, without going, so this is the way you don't need to go to small h. And anyway, let's think of this as a filter. So we plot the big H of j omega as a function of omega. Then its complex value is well j times omega. So we plot its absolute value and angle. Then we see that in terms of absolute value, big H of j omega is omega, absolute value of omega, so it's omega and then minus omega line. Okay, and in terms of angle, then when omega is greater than 0 is pi over 2, and omega less than 0 is minus pi over 2. Okay, and so I guess we can see it's kind of like frequency shaping. If you look at the amplitude, so it's frequency shaping kind of this way. So when your omega is small, then the amplitude gets smaller, and when omega is larger, your amplitude gets bigger. Okay, so you see that differentiation will highlight the high frequency component of your signal. And remember before, okay, and here is an example of a differentiation, but a bit different because we actually do it 2D signal. Yeah, as we said before, differentiation will highlight the high frequency signal, so it will highlight all the edge of your picture. So this is the original signal, and then this is the output with differentiation. Okay, and another example that in this current case is averaging. Okay, so averaging is like the reverse of differentiation, but Oh, sorry, that's summation. But anyway, averaging is very different from differentiation, and let's see what happened to averaging. Okay, so averaging signal we define is here is averaging of x over n, x over minus 1, just averaging over one time step. So y of n equal to 1 over 2 x over n plus x over n minus 1. Okay, and here we use the brute force calculation. So we use h over n equal, we calculate small h over n first. So you can just do by linearity and kind of know that x over n has h over n equal to delta function. This is the identity channel, and for time delay you have delta over n minus 1. Okay, then we use our explicit formula big H from small h, so big H over e to j omega equal to this summation n from minus infinity to plus infinity, small h over n times e to the minus j omega n. Okay, and yeah, so you sum minus infinity plus infinity, but you have a two delta function, and so you only need to sum for n equal to 1 and n equal to 0. Okay, so n equal to 1 you have 1 here, n equal to n equal to 0 you have 1 here, and n equal to 1 here you have e to the minus j omega. Okay, and you have this thing, and you kind of make it a bit nicer, then you can take out this e to the minus j omega over 2 factor and get a cosine omega over 2. Okay, and anyway, this is a convex value once again, and you can plot this as a function of omega. So the absolute value will be just the absolute value of this cosine omega over 2, and so this cosine omega 2 will look like this, and this is a periodic function with a period 2 pi. So only plot from minus pi to pi. Okay, and and for the angle is e to the minus j omega. Angle is minus omega over 2, so it is a straight line here. Okay, and yeah, so this function, this system will shape our output frequency like this. So you see that for the low frequency component, it kind of stay the same, it has amplitude 1, and then the high frequency component, so remember for discrete time high frequency and plus minus pi, high frequency component will be suppressed. So high frequency component and exactly pi plus minus pi will actually totally got eliminated, it becomes 0. Okay, so yeah. So I guess it's time to take a break now, and we'll come back in 10 minutes to talk more about filtering and try to start the introduction on Fourier transform. Okay, let's take a break for 10 minutes.有问题吗？没有。 哦，好，贴上一点，等一下啊。要问这张图吗？还是
这张？
这个好啊。
就是它这边是直线，为什么它加这个直之后会是一个？这为什么会这边翘起来？
翘起来，为什么会翘起来？
为什么它不是这样，然后就变成这张图？
因为这个是 H of。
没有，这个是角度嘛，就是角度是图派在转的，它因为是 equal 是 j omega 除以2，所以它不会翘。首先这个没有绝对值嘛，所以角度本来就是这边是负的嘛，就是 omega 是正的时候 man 是 omega 就是负的嘛，然后 omega 是负的 man 是 omega 正的，然后它不用翘起来是因为角度是图派在转的嘛，就是应该是在这里，我想想看啊。讲的我自己都有点混乱。这个
为什么直接会变负的？这个负的到底是哪一个？
没有，这里有个负号嘛，所以本来就应该要负的。
可是它不是在 exponential 的东西上？
对，没有，这个是角度啊，这个是角度，所以这个也在 plot 的是负 omega over 2。这个是角度。
这个是在讲这个。
负 j omega。
那这个是在讲。
这个是在讲这个的绝对值嘛，然后绝对值这里就没有，这边 cosine omega over 2。
所以它就会在所以这边就是这个东西，然后这边是在讲它的角度这样。了解。
然后
这边指的是这整个的值。
对，那这边在讲
单纯只讲
这个东西的角度。
对。然后他有点讨厌，还有一个
讨厌。
没有，他是因为这个我们在说它是 periodic 嘛，然后 periodic 它正负有点复杂，就是 cosine omega over 2它是这样子，然后再这样子上来嘛。
对。
然后你会说这个东西跟这个东西长得不太一样，然后他会做的事情是然后这里也是这个，就这里是有点负的这种感觉吧，就是这里你直接 periodic 它会接上来嘛。然后这里你在 periodic 的话，其实会再接下来一段，因为它要2派一个区间才会回来嘛。因为角度的话是加2派没有变嘛。但是你会发现这个区间没有到2派，这区间只有派而已，所以这里的负的跟这里的多下来一个派会互相消掉这样子。懂。
你们懂吗？有懂的可以。
没有懂。等一下，
想知道他
就是
讲什么，但我不懂。
有点服务的这。
我也在懂他讲什么，但是
我知道他最后是要凑到兔拍，但
这个兔拍不是指这边吗？
不是
有2个兔拍，上下的角度也要兔拍嘛，就是你想象这条线继续画下去的话，它是会无限延伸上去，无限延伸上去的嘛。对啊。然后我说，那一条无限延伸的线显然不是 periodic， 那我们要怎么硬说它是 periodic？ 有人说它是 periodic 的 period 2派嘛。对。所以我画黑板好了。还是我画在这里好了，这样以后才看得到一个稍微复杂的东西。所以这个东西我们说，画这不知道够不够大这个东西如果画个示意图，所以如果我们一直 periodic 延伸下去的话，会是这样的东西，这样子嘛，这样子。然后下面这角度如果 periodic 延伸的话，会变成这样的东西，这样的东西。然后我来说为什么这个是 make sense 的事情。首先直接把它看成 periodic 是这样子嘛，但是你去对应到这里的时候，你会发现长得有点奇怪。首先 cosine 方向就不是长这个样子，对吧 ？cosine 应该是上下的。然后另外你会说为什么这里我可以把它切断变成这样子嘛？因为如果它就只是这个负 j omega over 2的值，它不是应该无限延伸的嘛？对。然后所以有2件事情吧。一件事情，首先是负 j omega over 2的事情，为什么可以无限延伸会被切断？ 是因为这里的上下有 periodic， 因为它是这里讲的是角度嘛，这里讲的是 e2 的 j 西塔的角度嘛。那这个西塔的角度当然是因为它是那个复数的相位，那它等于0是等于2π嘛，因为它是在讲说 complex plane 上面的这个角度，所以你的0度是等于2π的，所以这个角度的轴自动就有一个2π的 periodic， 所以你从下面到负2π就等于到0这样子。
OK，
所以你可以把这里切断贴上来。你就是你每走一个2π你就可以贴上来，每走一个2π可以贴上来，每走一个2π可以贴上来。对，但是我在说这样子，你直接去贴这2π上来的话，你发现这里不对，因为这里还没有走到2π，这里是只从 π/2 走到负 π/2， 这里只走 π 而已。为什么你只走 π 就可以贴上来？是因为只走 π 贴上来，那里插了一个负号，就是把这个 cosine 这里的负号贴翻上来。对，所以这里有一个负得正的事情。
我懂了。
你懂吗？
我懂为什么是这样，但没有懂为什么要这样。
就只是 notation 啊。
OK。
就其实只是因为我们在把复数写成比较复杂的东西，所以贴的有点奇怪，但是基本上就是长这样跟长这样子，然后一直 periodic 它没有错这样子。对啊。
我可以听一下你理解什么吗？
可能等一下我们再讲笑话。对。
它就会变2π，然后因为你把它转上来，所以它本来是这样下来，就这边有个负嘛，然后因为你这边要给它贴成2π，所以你就得在这边加一个负号，然后所以它就转上来。你知道这样吗？你可能要，为了因为你为了要把这个变2π，
我为了要把这个变成2π，
所以你要再多一个π。那你再多一个π的话，你这里就要加一个负号，所以你就要把它转上来，那就变这样了。对，跟那个差不多是这样。
差不多这种感觉。
这个就不知道。
这很重要。
还有
翻上来。
还有，就还有。
没有重要就是，只是在解释它真的是漂亮。
那为什么我要把它补成2π是翻上来？
因为你只能在2π的地方把它切断嘛，因为不然你一条直线你没有理由可以把它就是切上来，就是你可以把它切上来，理由是因为角度加的2π是没有变的嘛，就角度任意加减2π是没有变的，所以那条角度的线你可以在就是每2π的地方就把它剪断，然后贴上来这样子，剪断往上移2π这样子。但是我们移的数字不是2π，我们移的数字是π，所以它要多一个负号这样子。对，对，厉害。好，I think it's time to get started. Yeah. Okay, let's get started. Yeah, so we have a bit of detail on how this thing is actually periodic. Period 2π is not a problem. And anyway, you can check it out yourself. And it's those two pictures are correct as a I guess as a conclusion. Okay, and let's go back to filtering. Okay. And let's talk about filters that I guess the most well-known filters that people like to talk about are those frequency selective filters. Okay, so the frequency selective filters are filters that will select some band of frequency. Okay, I guess the example here is a polyphasor. So a filter is a little TI system that has your HOJ omega look like this. Usually it don't have any complex value, it's just real HOJ omega, and it will look kind of like a black wave. And so some of it will be 1 and some of it will be 0. And then this 1 region is called pass band, and the 0 region is called stop band. Okay? and this is the ideal frequency selective filter. And those things, so this is ideal, and so usually it's this is now we are going to engineering mindset. So usually it's that you want your system to have this property, and you will piece together electronic components, and to have your system have this kind of behavior. Okay, and it's very nice. It was so as they say, it will select some frequency of your output signal. So your input signal has some frequency component in the passband. Then because the response is 1, it will perfectly pass through. And if you but for the component in the stopband, the output will multiply by 0, and the output will become 0. Okay, as we say here. So remember, in a LTI system, we have that different component will get multiplied by different h of jk omega naught. Okay, so if your k omega naught is inside this passband, then your ak is unchanged. And if k omega naught gets hit by the stopband, and the output will be 0, and we call those components get filtered out by this filter. Okay, so anyway, so here is ideal low pass filter means that low pass means that you pass through some low frequency signal. Okay, so your pass band is centered around 0. This is for continuous time case. And well, low frequency is obviously means that your frequency is lower than some cutoff frequency, omega c to omega c to minus omega c. And so this is low pass, and naturally they are high pass filter. So high pass means that your filter will pass all the frequency higher, all the component higher than some frequency omega c. Okay, so larger than omega c or lower than minus omega c. Then you can also have band pass filter. Those are really arbitrary. So here we have some band pass between this omega c1 to omega c2, etc. Okay, and here we have some side note here. We have seen that we have designed all our filters to be symmetric around 0. So the big H is symmetric around omega equals 0. And we want that because we want the real signal to stay real. So we want, because real signal, we want A star of k equal to A minus k. So we want the amplitude of AK and the amplitude of A minus k to be the same. Okay. So yeah, so you have those filter, real signal will stay real. Okay. And so that's for continuous time ideal filters. And we also have discrete time ideal filters. And the different part is, remember, pH of omega is now periodic with a period 2 pi. And so low pass filter is periodic signal, so it actually is a periodic block wave. And once again, it's only pass the signals around 0, but then you should also pass signal around 2 pi and minus 2 pi, etc. And for high pass filter, then high frequency component are those odd multiples of pi, so it's only pass the signals that's around pi or minus pi or etc. And then you also have the band pass filter, and it's filtering at the arbitrary location, but we still want it to be symmetric around omega equals 0, and it is periodic with period 2 pi. Okay, so those are ideal filters, and then we give some example of the construction of filter. So those are very naive attempt to construct filter, but by a very simple electronic system. And obviously there are better ways to construct filters, but I guess we will not actually those are in the textbook, but the chapter unfortunately will not cover them. Okay, so but you can look at the book for better filters. Okay, but anyway, let's back to our very simple RC low pass filter. So the filter is just this thing. It only have I think is two or three components. So you have the input as is a voltage here, and then you have two components. So you have a resistor here and a capacitor here. So input signal is the voltage here, and the output signal is the voltage around the capacitor. Okay. So it's a very simple component. It's RC circuit, and we'll see that it's a low-pass filter, somewhat. Okay, and so we derive this big H with this kind of a cheating equation once again. I guess not cheating, but it is a shortcut way. So we just say our input is e to a j omega t, and we see what's the corresponding output. And anyway, this system can be, you do the physics, you see that you can be described by this. It can be described by this differential equation, and then assuming initial rates, then we know that the input and output should satisfy this equation. So input should be e to a j omega t, and output so by initial rates, the system is LTI, and so input and output should be able to describe this way. So output is big H times e to a j omega t. So yeah, we plug in then here. So the output here is big H e to a j omega t, big H to j omega t, and the input e to a j omega t. And then we see kind of checkouts. So differentiation here, you get the h r j omega here, and then you see both sides has this e to a j omega t. You can cancel out, and you move things around. You see that so you have big H here. So you add together the coefficient and throw in the other side. It's OC coefficient 1 plus RC times j omega. Okay. And you see that your h of j omega is 1 over 1 plus RC times j omega. Okay. And big H. So yeah, so this is our big H. We'll calculate big H. And I guess I'll talk about here. So we can plot our big H because of explicit formula here. And for our filter perspective, the most important thing is here. So I guess it's not totally ideal because when we talk about filter, there are different parts. It's not totally ideal. Okay. So so big H. So we think about is absolute value. Then it's look like this. So you see that you plot the absolute value of this thing, look like this, and you see that indeed is filtering or is passing through more of the omega the low frequency component. So for omega around 0, the absolute value of H is higher. Okay, but and you see that it kind of cut off. So it's not a hard cut off as we have in the ideal filter, but you see that it kind of starting have decay with around this 1 over RC point because you have RC here. Okay, and but so there are, I guess, two ways not ideal. So first is the angle is not 0, so we still have angle here. So you plot the angle of this thing is from minus pi over 2. Sorry, from pi over 2 to minus pi over 2. And also, as we said before, it's not cut off. You have this basically 1 over omega decaying cut off for your absolute value of H. And then if you do more calculation, you can calculate small h of t and the step response s of t. Small h of t, on next chapter we'll talk about how to calculate small h of t from big H of t, big H of j omega. Right now we only have the equation from small h to big H. Okay. In next chapter we'll talk about how to calculate this. But anyway, so here is the calculated result, and you can plot it here, and we plot it here. So small h is this exponential decay function, and we also have unit step response. Okay, and we see that we can tune our parameter in our low-pass filter by changing our RC. Okay, so we have this tau equal to RC here. So we see that when RC gets larger, then this filter will, this signal will, again, this function will start decaying faster. So you have a narrower pass band, and but also that will give us a longer response time, okay? Because this thing is RC here, so we actually have engineering trade-off here. So if you want the filter to be more sharp, so if you're filtering a smaller range of a signal, then you want to increase RC. But that will also increase your impulse response, will make your impulse response decaying slower, and that means that your signal will take your system will take longer to go to steady state, and and that usually means that your system will have more oscillation, etc. Okay, so there is an engineering trade-off of how you want to set your RC. Okay, RC value. Okay, and but anyway, here is a bit of summary of the calculation we do in the last example. So we are saying how you derive the frequency response from the differential equation with constant coefficient and initial rates. And the way to do it is just assume your input and output is this complex exponential and eigenvalue times complex exponential pair. And you plug in those into your differential equation, and you should be able to solve for your H over J omega. And then on the next chapter, we'll talk about how you get a small h over t from your big H over omega. And that will actually become our way to solve our linear differential equation. Okay. And but let's get back to filter. So that's a bit of a discourse to differential equation. So go back to filter. We see how to construct a low-pass filter from this RC circuit, and how do we construct a high filter? High-pass filter is actually with the same circuit, but we just change our output direction. So the same circuit, but now we say, what if we output from the voltage between these resistors? Okay, and then we write down the physics and write down the physics with this equation, and we do the same thing. So we have an input signal and the output signal here, and because it's kind of the same example, instead of big H, we see big J here, so big G here, so we have big G J omega equal J omega t, and this big G J omega equal J omega t, and once again, differentiation gives us extra J omega here, and they cancel all the e to a J omega t, and you move things around, you have G J omega equal to now you have h omega j omega here, because you also get differentiation on your input, and anyway you get j omega rc over 1 plus j omega rc. Then this thing, okay, so j omega equals this thing, and you can kind of feel when omega equals 0, because this is 0, you have 0 over 1, so it's 0, and when omega goes to infinity, it's dominated by the j omega rc. Then you should go to 1, both upper and lower. Okay, and so you plot this thing, and its absolute value and its angle. Then you see the absolute value is this kind of high filter thing. So frequency around 0, it got filtered out, and when frequency is higher than is 1 over RC, is approaching 1. And for the angle, then you can plot the angle here. Angle is a bit funny, but you can plot the angle here, and the angle as omega goes to plus or minus infinity, it should become 0 angle. Okay, and then we can also calculate the step response of the system. Then we'll look at this, and once again you see that you want the sharper filtering out, so you want the smaller 1 over RC, then you want the RC larger, and you will get a larger response time. Okay, and so that's a filter for continuous time. Then we have a filter for discrete time case, and it's and now it's not described by differential equation. It's described by difference equation. So it's very similar to previous part. We have that, I guess here. Yeah, and yeah, here we have example. So we say what over system, but now we don't have exact electronic circuit. We just say if our system is described by this difference equation, so y of n minus ay of n minus 1 equal to s of n, and we do the similar thing, similar 3-step to solve this difference equation. We find out that h of e to a j omega equal to 1 over 1 minus a e to a minus j omega. It's quite different because it's a difference instead of differential. And the difference just give you hr j omega e to a minus j omega here. So you see that when you take it n minus 1, you have n minus 1 here. So you get hr j omega here, vector here. Oh, sorry, this is h of e to j omega, and you get h e to a minus j omega vector here. Okay, and anyway, you can still also for your big H, and you get this 1 over 1 minus a e to a minus j omega. And this is more complicated because you have this e to a minus j omega vector. But anyway, you can still plot it here, and we plot here for two different a. Okay, so you see that for this positive a equal to 0.6, it's like a low-pass filter. Is the absolute value of h is higher when omega is around 0, and yeah, and you can think about it's about 1 minus. It's 1 over 1 minus a here for positive a, so it's higher. Okay. And for a negative, so a equal negative 1.6, then around 0, then is 1 over 1 minus a, and by a is negative, so it's 1 over 1 plus 0.6 here, so it's actually lower when omega is around 0, but when omega is around plus minus pi, then is e to a minus j omega give you a minus 1, and you actually get 1 over 1 plus a here. So it's 1 over 0.4 here. Okay, so you see that the amplitude gets higher around this multiple of pi, and so this is a low-pass filter when a equal to negative, and high-pass filter when a is negative, and low-pass filter when a is positive. Okay, and also we plot the angle here. Okay, and yeah, so you see this founding notation here. Actually, check out you have this founding e to a minus j omega, and this kind of ensure that your big H is periodic with period 2 pi, because you have e to a minus j omega here. Okay, and yeah, and we can have another filter that's this finite impulse response filter that's a non-recursive filter. Okay, so here we only have y of n, so we don't have any time difference on y of n. We just have y of n equal to different time delayed of x of n. Okay, and and then we also have a different way to calculate the frequency response big H. We also do this in continuous time case 2. So here we basically calculate small h first and calculate big H from small h with this explicit formula. And to calculate small h, we substitute a big X with small x with delta of n, and we can calculate small h. And so we see that with this linear simple system, we can calculate small h quite quickly. So we substitute the small x with delta, and we get small h like this. Then you calculate big H from this formula. Because you are summing a whole bunch of delta function, it's really simple. Okay, and so you have this big H, and yeah. So we see that big H is the summation bk to a minus j omega k, with the same bk as this bk in your system equation. And one of the system that we see, I guess one of the usual choice of this bk is you pick y of n as the average of x over n minus k. Okay, so bk is just 1 over n plus 1, where nm is the range here. Okay, and so this bk, so this y of n is just the average of x of n from minus n to big N, from minus big N to plus big N. And so you calculate your h, and then you see this is where the sine over sine function. So this is a moving average filter, and it will look like a low pass filter because you apply your big H, its angle. It's now sorry, it's still not real, okay? But it's plot the absolute value of H, and it will look like this. Okay? This absolute value of the sine over sine thing, and you see that they are concentrated around omega equals 0, and then you can change the parameter. You are averaging more. If you are averaging over averaging over a larger range. So here, remember the n and m are the upper bound and lower bound here. Okay, and so you see you are averaging over a larger period, then it's getting more narrow. You are then, yeah, and intuitively check out because this is averaging function, so it should be smoothing out your signal, so the high frequency component will get averaged out and suppressed, and you are left out with your low frequency component. Okay. And anyway, here is a summary of what we do in the chapter. So we show that this e to st and z to n are eigenfunctions of a LTI system, and we call it eigenvalue big H of s or big H of z. And to write things into linear combination of those e to st or z to n, we derive those Fourier series representations. So, and they are for periodic signal. So for periodic signal, we have that continuous time x of n equal to summation k, ak equal to jk omega naught t. And this one case is similar, but your ak is over one period, of big N. And you can calculate ak for continuous case with this analysis equation. 1 over t integration over one period x of t e to the minus jk omega naught t dt. And for this ground case, ak equal to 1 over and the summation over one period x of n e to the minus jk omega naught n. And we see that let's plot. So once we decompose our signal into this linear combination of ak, then we can just write all the output signal with bk equal to h of so this big H of j omega naught k ak. Okay. And the last sample either continuous time case or discrete time case. Okay. Any question with this chapter? If okay, then we have 25 minutes to start chapter 4. Okay, so I guess we have a pretty good transition of chapter 4 here. So we see, basically we have the same idea. So now we see that decomposing things into this complex exponential are very nice. They let us write down the output with this simple way. And but we're seeing that for Fourier series, we can only do them on periodic signal. And so on chapter 4, 4 and 5, we are going to derive Fourier transform, which will tell us how to decompose a periodic signal into into a linear combination of this e to a jk omega t. Okay, and yeah, so let's start doing that. Let's go to chapter 4. Let's try to not crash this. Cancel maybe chapter 4. Okay, let's see. Okay, the continuous and Fourier transform. Okay, there are a lot of things we'll talk about here, and let me get the streaming correct. Okay, seems to be working. Okay, chapter 4, continuous and Fourier transform. Okay, and yeah, so I guess I'll start the derivation. How do we get get the representation of a periodic signal as a complex system nature. That's a continuous time Fourier transform. And here we'll do a bit of ad hoc derivation, okay? Because this is continuous thing. And basically what we do is, we do kind of infinitesimal step discretization, okay? And I guess we start with knowing this Fourier series representation. So we have the Fourier series representation of a formula, okay, for periodic signal, okay? So x of t summation ak equal jk omega t, ak is the integration x of t to a minus jk omega t. We just seen this, okay? And so what we will do is we start with this Fourier series representation, and we try to take this period t to infinite. Okay, so we try to take this period big T to infinity, and we think about signal with infinite long fundamental period is basically a signal with that's not periodic, okay, or aperiodic, okay. And then and remember this k omega naught will become the frequency. K omega is already the frequency over the harmonic component, right? So x of t is summation over different harmonic component, and then remember this k omega is the frequency over the harmonic component, and in the end this k omega will become the omega of our Fourier transform. Okay, and so what happens is as we take t to infinity, then omega naught will go to 0 because omega naught is 2 pi divided by t, and so we get final and final sampling over those k omega naught. Okay, and so I guess I'll start with this ad hoc derivation. So we start with this synthesis equation for Fourier series representation. Okay. And we know the output will be t equal to ak h over jk omega naught t equal to k omega t. Okay, this is nice. I guess we don't need this y thing. Okay, and anyway, we have this Fourier series representation, and we start with some intuition on this block wave signal. Okay. Or we try this periodic block wave signal. This T1 minus T1 to T1 block, and with the period big T. And we have calculated Fourier series coefficient AK is this thing. Is a sinc function sine k over k. So sine k omega. Here we actually need to see the detail here. So AK equal to 2 sine k omega naught T1 over k omega t. Okay. And so we can describe this with envelope function. Okay. We see this AK, then we think this as we find out this can be written as this funny way. We can read it as a function of omega. So we think this k omega as omega. Okay. So this is sine omega times T1 over this is sine omega T1 over omega, and sampled at omega equal to k omega naught. Okay, so here we are just rewriting this AK, and but we see this AK is a very particular form of its dependence on k, because all the k is attached to this omega naught, right? So, and we already know, so remember before, k omega naught is some special k omega naught should be the frequency of the harmonic component, okay? So we see that this AK can be written as kind of, in terms of the frequency k omega naught, and so, and we also move t to other side. So tak equal to this sine omega times t1 over omega function. And when we want this for a particular k, we just sample at the k omega naught. Okay, and what's nice here is that we write this, we put in this form. Then you see this sine omega t1 over omega function has no dependence on t over omega naught. Okay, So when you change t or omega naught, this thing doesn't change at all because it just doesn't. Okay. Okay, and only the change. So you see that when you change t and omega naught, how you change ak is, well, the t will get larger, and also you are sampling with smaller omega naught, right? So each ak is at a different k omega naught, but this omega function itself doesn't change. Yeah? And so we can think of this as the envelope of tak, and tak samples this 2 sine omega t1 over omega. And I guess we say a lot, but we should see the picture first. So we plot this tak here, so this is sine omega over the sine omega over omega function. Okay, and remember omega not equal to 2 pi over t. And so we see that for different big T, we are just sampling AK with a final point. So here we have a different omega, we have different T. So first, this plot is T at 4T1, and here is A0, A1, A2, A3, A4, A5, etc. And then we have larger T, then T equal to AT1, then we have A0, A1, A2, A3, A4, A5, A6, A6, etc. So we see that this enveloping function doesn't change, and your AK are just sampling your envelope function and the final grid. And yeah, so we see we double big T again, so T becomes 16T and T1, and so omega naught should be divided by 2 once again, and you have twice as many sampling again, etc. And yeah, so this point is 2 omega naught, and it becomes 4 omega naught, and this point becomes A omega naught. So this was A2, and it become A4, and it become A8, etc. Okay. And so what I want to say here is that now we consider t go to infinity, then we kind of feel your tak should be just this whole envelope function. This is 2 sine omega t1 over omega, because you are sampling at basically every point of this function. Okay, and yeah, so this is what we say. So as t goes to infinity, your omega decrease, and your sampling is closer spaced, and you think your Fourier series coefficient should approach this envelope function 2 sine omega t1 over omega. Okay, and also as big T increase, so we are fixing t1 but just increase t. You think about if you fix t1 and increase t, then the spacing between this period gets larger and larger, and your signal looks more and more like an aperiodic signal, with just a block of t1 here, and because you go to t to infinity, and you kind of never see you repeat yourself. Okay, and yeah, so we'll do a general derivation with this idea. So we say we have some signal with some finite duration, and we try to derive Fourier series representation. So we have some finite duration signal from -t1 to t1, and we want to see derive a Fourier series representation, Fourier transform, Fourier transform representation, and we start with the periodic signal. Like this way. So we say we can try to copy and paste this signal to make it periodic. So we repeat it with some period big T, and so the finite duration signal was called x of t, and this constructive periodic signal we call it x tilde of t. Okay, and so x of t is 1 period of x tilde of t. And we think if we just take a big T to infinity, then x tilde of t should become x of t. Okay, and so by x tilde of t, what we want this is because it's periodic, and we can write down the Fourier series representation. Right, it's ak, and then we'll take a big T to infinity, and let ak become the Fourier transform of our x of t. Okay, let's see how this goes. So x tilde of t is we can write the Fourier series representation. So we have the synthesis equation and the analysis equation here. So AK is this integration. integration over one period x tilde of t. Okay, and okay, so we start with this AK equation. Then this AK equation, we see something funny. It's over one period, so period from t over 2 to t over 2. Okay, so this one period integration. But we see that in terms of this integration period, integrating over x tilde of t and integrating over x of t is the same, because it's the same signal over one period. Okay, so we can change this x tilde of t to x of t, and then we do something very funny. Okay, and because now we are only integrating over x of t, we must will change the integration from minus infinity to plus infinity, because now you are integrating over this one period, but there is nothing outside, so you can integrate from minus infinity to plus infinity. Okay, so we see that AK is 1 over t integration minus infinity to plus infinity, x over t then times is e to the minus jk omega t. Okay, and now just like our block wave example, we define the envelope function. Big S over j omega equal to big T times AK. Okay, then we see that, and this thing. Okay, so envelope function T times big T times AK, and we call this big S of j omega. Okay, and so big S of j omega. This thing we find out that indeed it's only a function of omega, so it's the integration of Ox of t and e to the minus omega t dt, where we have used that we say this k omega naught, we defined it as omega. Okay, and you see that indeed this is only a function of omega, just like before, just like in this envelope function. We find that the TAK is a function, only a function of omega, and here we see that explicitly this thing is only a function of omega. It's the only function of is k omega naught, and it has no other dependence on big T or omega naught. Okay, because here x of t and x of t has no dependence on big T. It was the starting function we have, and the e to the j omega t is no factor of big T. Okay, yeah, x over j omega is independent of big T. Okay, and yeah, and now with this envelope function, now we try to write everything in terms of x over j omega. Okay, so okay, excuse me, I need to the battery. Let you guys stare at this very beautiful big S over j omega. So this big S over j omega will be, the spoiler is that it will be our Fourier transform, because it was an enveloping function. It is an enveloping function over our AK, and we'll think this is the Fourier transform of our x over t. This is basically just like AK. This is the amplitude of x over t on the component e to the j omega t. Okay, and anyway, let's go back to algebra and see how the algebra all work out. Here we define x over j omega as this integration x over t to minus j omega t dt. And then we try to replace all the things with a big X. So first we do AK, that's a very simple, AK equal to 1 over t big X. Okay, just from this equation, reverse it. And and now we can, yeah, so now we have AK, then we can replace our synthesis equation of our x tilde of t. Okay, so synthesis equation, so yeah, synthesis equation says that x tilde of t is the summation ak to a jk omega naught t. And we have ak in terms of big X, and we have x tilde in terms of big X. So it's 1 over t big X e to a jk omega naught t. Okay, and then we do something very funny here. Then we replace this 1 over t with 2 pi omega naught divided by 2 pi. Then so we have 1 over 2 pi here, and then we have omega naught here. Okay, so x tilde of t is 1 over 2 pi, then summation k, big X e to big X of k jk omega naught, and e to jk omega naught t omega naught. Okay, and now we think about how this summation to go to what's this summation when t go to infinity, and so now get kind of hand waving argument. Okay, as t go to infinity, we actually say this summation go to. Okay, so there are two things happen. Okay, so as big T go to infinity, so left hand side is easier. So let's say it first. So left hand side x tilde of t should go to x of t. That's what we say at the start. Whereas the x tilde of t, let's go back. Okay, because x tilde of t was x of t with period with the copy paste period big T, and we think when big T go to infinity, then all those copy paste go to plus infinity minus infinity. So x tilde of t will look like x of t. Okay, so t go to infinity, x tilde of t should become x of t. And on the other hand, so that was the left hand side. On the other hand, we argue that when big T go to infinity or omega naught go to 0, this side should become an integration. Should become this integration of x of j omega e to j omega t. And that's because, so first this all those k omega naught factor become just omega. So we think k omega naught, we define it, we have a view length as omega. And so this big X is big X over j omega, and this e to j k omega naught t is e to j omega t. And then this omega naught actually become d omega because because omega naught was the step that you sample omega on this omega line, right? I guess it's still better to say the picture, because here we plot this function. So this big X e to j omega t as a line here. Okay, let's ignore that there is a complex value, so we can plot a complex value here. And anyway, so we have a line here, and as a function of omega. And what this summation here is you are sampling this function at a value that's a k omega naught, because k was integer value. So at every omega naught, you are sampling this function, and you are calculating this area of those rectangular. Okay, so the height is this big X times e to j omega t at omega equal to k omega naught. So for example, we have an example here. So it is some k omega naught, we have a height being this value here, and the width being omega naught. Okay, so we see that the summation here is summing over a whole bunch of rectangular area here. And then you see that as omega naught go to 0,